ahead and get started. Last time we already talked about the search algorithm. Do you guys have any questions back there? No? Okay, so please stop chatting. Okay, thank you. So last time we already talked about the array search algorithm, and I said the algorithm that I wrote is perfectly fine, even though it seems like there's a problem. So let's go back to that algorithm, and then we'll start from there. So go back to the website. And I think I just uploaded the notes from the other day. So it's all here. I just need to copy and paste the last portion. This is our algorithm. We'll use a text editor for today's note. Right there. Okay. When you look at this algorithm, it seems like we have a problem. Because if you think about it, what if I becomes bar a bar? When I becomes bar a bar after I gets I plus 1, we have to go back to this line here, and then we have to evaluate the conjunction. When we evaluate the conjunction, the first part is okay. When I equals to bar a bar, this part will just return a value of false. Okay, so no harm is done. But the other side, when I equals to bar a bar, then we'll be trying to access a bracket bar a bar close bracket, which is an element that does not exist. Okay, so we'll be trying to access an element that does not exist and try to compare that to the value that we are searching for, and therefore we might have a problem. But in reality, in almost every modern programming language, this is not an issue anymore. Okay, it's not an issue because we have what we call short-circuit evaluation, or otherwise known as the lazy evaluation method, in which if you can determine the result of this entire operation by looking at only the left-hand side, then the right-hand side does not even get evaluated. Okay, does everybody understand what I just said? Okay, let me just say it again. When we evaluate a conjunction, which is an AND expression, if the left-hand side is false already, I do not even bother, or the computer would not even bother to look at the right-hand side. Does that make any sense? It makes sense because in order for the entire expression to be false, what do you need? Just one of them to be false. Okay? So if I know the left-hand side is false already, I don't need to look at the right-hand side. Yep.
So let's assume that I is not less than bar a bar. Mm-hmm. If it was to evaluate the right-hand side first, it could go on indefinitely because it's looking for an element that doesn't exist?
Then we get back to the problem that we have talked about, because you're trying to access an element that does not exist. So there are three possible cases. One is the C case. In cisp360, the C programming language will try to access a location that is not a part of the array A and try to compare using that location. Comparing using the wrong location is not as big of a deal because it does not cause any corruption. If you're using VB, it will give you an error message, a runtime error, and say that you're trying to access an element out of bound. If you're using PHP or Perl, it will create that element on the fly, and the loop becomes an infinite loop. So neither of those three cases is what you want, but in this case, because it will stop as soon as it has evaluated the first part or the left-hand side, so it's not an issue. Okay. So now we go back to our notes here. And I will just point out which module talks about this so that when you want to study, you know where we are supposed to go. Okay, short-circuit Boolean operators. That's the topic. So here's an example, which is exactly the example that I have a little bit earlier, except in this case I use the math symbols instead of the easier symbols to understand. This is the conjunction, and the rest of the algorithm is exactly the same as what we talked about on Tuesday. So in this case, conjunction is no longer commutable. Okay? When you look at conjunction, it normally is commutable. Let me just use a text editor to describe what is commutable. How many people still remember what commutable means in algebra?
Commuted property?
Commutable, yeah. Okay.
Equal on both sides?
No, it means you can exchange the order of the operands or the numbers that you're dealing with. Okay, so I'll just say that conjunction is normally commutable, which means A and B is the same as B and A. Okay, it's kind of like multiplication or addition in arithmetic. They are all commutable, which means you can change the order of the numbers and it comes out to be exactly the same. Subtraction is not commutable because if you change the order, if you change the position of the two numbers, it doesn't come out as the same number. It comes out as the negation of the original calculation. Division is not commutable. Okay, it comes out as the reciprocal of the original intended result. But conjunction is commutable. Now, how can I prove that conjunction is commutable? Well, remember the truth table. Okay, we have A, we have B, we have A and B, and then we can have B and A. How many values can A have? It's Boolean. It can have true or false, right? When A is true, B can be true, B can be false. When A is false, B can be true, B can be false. In other words, these four lines, this part of the table enumerates all possible inputs to a conjunction with two variables. Is that okay so far? You cannot do this trick with arithmetic operations because there's an infinite number of integers, and you cannot just say you cannot list out and you enumerate all possible cases. Okay, in the case that A is true and B is true, what is A and B? True. What is the result of B and A? True. So without having to spell out the exact reasoning, we can figure out the rest of this table. So after you figure out the rest of the table, all you have to do is to compare this column with A and B and the other column, which is B and A, and they look exactly the same. And that is enough proof that conjunction should be commutable. Okay? However, with short-circuited evaluation, conjunction is no longer commutable. Okay. And that's because if you look at our example here, if I exchange the order, if I evaluate A bracket I does not equal to K first, and then I evaluate I is less than bar A bar, then I will still be accessing an element out of bound. Because I don't have the first condition. If I reverse these two, then I won't have the protection anymore, because when a programming language evaluates a Boolean expression like this, it always evaluates from left to right. Okay, it's the same way that you read a program, it is always from left to right. So that means if I exchange the order and evaluate A bracket I does not equal to K first because it is on the left-hand side, then I will still be accessing an element out of bound because I do not evaluate the other one first. So that means this is the right order. If you switch the order, it is incorrect. Okay? Is that okay so far? Does everybody understand what I just said? That when you exchange the order, the program will not work properly anymore. So back to the example, this is a full explanation of what happens. So essentially when we evaluate the conjunction, which is I is less than bar A bar, the one on the left-hand side, if the result is true, then we have to evaluate the right-hand side, because true and anything is the right-hand side. On the other hand, if I is less than bar A bar is false to begin with, we can conclude the entire expression itself is false, and then we can skip the evaluation of the right-hand side, and we can get out of the loop right away. So that's why short-circuited evaluation is useful. Let me ask you another question. What happens when we do not have short-circuited evaluation? In other words, what if conjunction always evaluates both the right-hand side and the left-hand side? How would you write the algorithm for searching for an element in a loop in that case? So let's go back to a text editor, and then we can just try to figure that part out. This is the algorithm that is short and concise because of short-circuited evaluation. So if I am going to, how can we rewrite this algorithm if there is no short-circuited evaluation? That's the question. Okay, yep?
Can you have a while after it? So do a while this, then do an indent while this, then do the next step?
Not sure exactly how you want to position things, but that's kind of the idea, is to break it up. Okay,
Yeah.
the idea is to break up I is less than bar a bar, and a bracket I is different from k. You do not want to evaluate both of these in the same expression. Okay, that's the idea. But it becomes kind of difficult to do it because the loop does have two exit conditions. The loop wants to exit when we are at the end of the entire array. That's what the I is less than bar is about. But we also want to get out of the loop as soon as we find an element that matches what we're looking for. Okay? So that makes it kind of difficult to separate these two because they are both conditions that we can use to get out of the loop. So the answer to this is we have to introduce a variable. Okay, there's a way to fix it, but we have to introduce a variable. So to do this, we have to introduce a variable to replace one of the conditions in the conjunction. That's how we can do it. Okay. So that means the algorithm is going to become something like this. I still gets initialized to 0. But now you also need to keep track of another variable. I will call this found. Found is a Boolean variable, which means it is only going to store either a value of true or a value of false. Okay, it can only have one or the other. And what we'll do is we'll assume that the item is not in the array. Okay, so we'll use a assumption and say that, okay, let's say so far we have not found the element that we're looking for. Okay, so we'll confirm when we find it, but as far as we are concerned at this point, not having looked at one single item yet, we'll just say that, okay, I don't think the item is in the array, so I'll confirm it when we see it. The loop now becomes the same, kind of similar to what we have before, and in this case, the order does not matter because we don't have short-circuited evaluation anymore. So we can say found and something or not found. Okay, so we say while not found, which means, okay, as long as the item is not found, I should continue to look, or at least, try to look. But at the same time, I also want to say I has to be less than bar a bar, because when I equals to bar a bar, I should stop as well. Okay? Is that making any sense? If you just look at the condition itself, does it make sense that when the item is not found yet, and I have not reached to the end of the array, let's go ahead and do some more stuff. Is that making any sense? Just from the perspective of just the logic. Okay. So inside here, we still have I gets I plus 1 because we have to move on to the next item. But before we do this, before we say I gets I plus 1, we also have to keep track of found. We have to update the value of found. So we have to say, okay, let's go ahead and update the value of found. And I would just say that found is a bracket I equals to k. And I will use parentheses to make sure that we understand that a bracket I equals to k is not an assignment, because when some people have backgrounds in programming already, and you can misunderstand this one is an actual assignment. So the assignment operation here is a bracket I equals k is actually the right-hand side of the assignment. It will return a value that is either true or false. That value will then be stored in found. So that means if a bracket I does in fact equal to k, then found will become true. Found will become true, I still gets I plus 1, and then when we get back to the beginning of the loop, because found is true, what is not found? What not found becomes false. So we have false on one side, but remember, this time we don't have short-circuited evaluation. We'll still evaluate the other side, but it doesn't matter because even when I equals to bar a bar, comparing I to bar a bar does not hurt anything. You're just comparing two numbers. So this is the solution to the problem that we have. when you do not have short-circuited evaluation. As far as I know, all programming languages today, have short-circuited evaluation. The only language that I have doubt about would be COBOL. I'm not sure, whether COBOL can deal with short-circuited evaluation. Pascal used to be the only programming language that does not do short-circuited evaluation. And today, since we don't use Pascal anymore, basically all practical programming languages, including VB and MySQL, and almost all variants of SQL, will do short-circuited evaluation. Are we doing okay so far at this point? Okay. Does anyone want to see this code traced? We can just use an array of 3 elements and trace it. Yes? Okay. Let's go ahead and do it. It's short enough and quick enough. It's not going to take a lot of time. So I'll just go ahead and type the program. Found is false to begin with. So we say while not found and I is less than bar a bar do. Do you want to use the same version that we have before, or do you want to use a more cumbersome version because there's a more cumbersome way to do it? No, just that one is fine? Okay. So we'll say found will get the result of a bracket I equals to k. I gets I plus 1, and while. And we'll start trace. On sheet 2. So this is basically what you have to do with your homework assignment, is to format your own sheet 2 for the trace. Anything that has loops or conditional statements, you have to have a comments column. You have to have a column for the line numbers. You have to have 1 column per variable. In this case, we have I, we have found, and then we also have the array A. So we'll just say that array A has 3 elements. Okay, A bracket 0, A bracket 1, and A bracket 2. We'll just say that we have to give this one initial values, and we also need 1 more column for k. Technically speaking, k does not need a column because it does not change over time, but might as well do it. So we'll just say that we're looking for the value of 2, and found does not start with any particular value. I does not start with any particular value, and that's our precondition for the entire conditional statement, for the entire algorithm. Okay. So this means that you have to set up your solution for the homework assignment kind of in a similar way. Yep.
Are we going to have to plug in the numbers for the arrays, or is it given?
I'll leave that part up to you to decide. Okay, when you look at the algorithm, you can always start with some known values and see what happens to the algorithm. Okay, because I want you guys to kind of get an idea of when do we need to start with some known values and when do we do not need to start with known values. So go ahead and do it either way, and then you will see whether you need to have initial values or not. In this case, we do, because we do not change anything in a bracket I. We only use it for comparison. So that's why we have to start with some values in a bracket, in the elements of A, because otherwise we cannot do the comparisons. Okay, so let's start with line 1. Okay. Line 1 is going to put a 0 into I. Line 2 is initializing found to false. Line 3 is the evaluation of the Boolean expression, which is kind of long. And we have not found. Okay, found is false. What is not found?
True.
Not found is true. Okay, not found is true. So that means, let's take a look at the other side. What is I less than bar a bar? I is 0. Bar a bar is what?
True.
Bar a bar is 3. 0 is less than 3 is true. Okay. Then we go to line 4. Line 4 is going to update found. What is it actually going to do? It's going to evaluate a bracket I equals k. That's the right hand side. I has a value of 0 at this point, so a bracket I refers to a bracket 0. A bracket 0 has a value of 5. So we are comparing 5 to k, which is 2. 5 equals 2 is false. So if the right-hand side evaluates to false, we will update the left-hand side to false too. So in this case, I have to write the false here. Even though found was false already, I have to write this false just so that I know that it's overwritten with false again. Okay. Then we go to line 5. Line 5 is just adding 1 to I. I goes from 0 to 1. We go back to line 3. Line 3 is evaluating not found again. Found is false. Not found is true. So the left-hand side is true. We look at the other side. I is 1 in this case. RA bar is 3. 1 is less than 3 is true. True and true is also true. We go to line 4 again. This time when we evaluate line 4, I is no longer 0. I is now 1. So when we compare A bracket I to k, we are comparing A bracket 1, which has a value of 2, to k, which also has a value of 2. In other words, we are evaluating 2 equals 2 in this case, which is true. The right-hand side is used to update the left-hand side, so that means found as a variable is now updated to have a value of true. Is that okay? That's the trick. Okay, that's the trick, because we have now separated the evaluation of I less than bar A bar from the comparison of an element to the value that we are looking for. We still have to go to line 5. Line 5 really doesn't do anything useful at this point, but we'll still have to do it. And then we go back to line 3. This time, not found is what? Not found is false, but I cannot stop now because I'm assuming that we don't have short-circuited evaluation. So I will still have to evaluate the right-hand side. I is now 2. 2 is less than 3 is true, but false and true is false. So that's why the entire expression is false, and I can get out of the loop at this point. Yep.
So this won't let you figure out which box it was in.
That is correct. It does not let you know which boxes it is in. It just tells you whether it is there or not. Yep. Do we have any questions about the whole concept of short-circuited evaluation? Now, if I can, this is not, okay, this is the solution when you do not have short-circuited evaluation. So the next question, let me save this file first, but the next question is, can we do short-circuited evaluation when we have disjunction instead of conjunction? I'll let you guys think about it as I save the file. So this is served without being lazy. Because the other name of short-circuited evaluation is the lazy evaluation of Boolean expressions. Okay, so the question is, can we apply short-circuited evaluation to disjunction? That's the question. In other words, if my expression looks something like this, okay, if my expression looks like I is less than j or k equals to 10, okay. Don't ask me why I'm using this example. It's just an example. So the question is, can I be lazy?
Yes.
I can be lazy, but it's a different kind of lazy. Because in this case, I can be lazy when I is less than j is true. Okay, because true and anything is true. So in this case, when the left-hand side is true, we don't evaluate the right-hand side. When the right-hand side is false, we have to evaluate the right-hand side. So this means short-circuited evaluation applies to conjunction as well as disjunction. It's just that when you apply to disjunction, the polarity is flipped. Okay, if the left-hand side is true, then you don't evaluate the right-hand side, because in disjunctions, true or anything is true. Okay. Are there any questions about short-circuited evaluation? No questions? Okay, if there are no questions about this, let me just make sure that I save it first to the folder So this way we don't accidentally lose it at the end. Okay. So getting back to the notes here, we're pretty much done with short-circuited evaluation. And life without short-circuited evaluation is the example that I showed you a little bit earlier. So that's all done already. And now we can move on to other search algorithms. Okay, we have already started on search algorithms. And so far in module 0060, we have only covered searching in an unsorted array. Okay, there's not much you can do about it. Okay, the only thing you can do is to get out as soon as you find something. But other than that, there's nothing you can really do to make it more efficient. So open frame and show display mode. That's all. But not. New tab. Okay. What about when we have sorted arrays? In other words, if I tell you that an array is already sorted, do you think there are situations where even though the item we are searching for is not in the array, we can still get out earlier? Well, let's think about it. It's all discussed, here, but let me just use the text editor to kind of give you an example of what I mean by that. Okay. So this is kind of like a bar to separate the short-circuited evaluation topic from the rest here. If an array is sorted, how can we improve the efficiency of searching for an item? That's the question. Well, the first thing we can do is we can improve the method that we have talked about so far. Let me give you an example. So let's say an array has the following values. So in this case, I'm not even going to tell you which one is a bracket 0. It's just in sequential order. Okay, so we have 3, 6, 10, 11, 25, and 36. Okay, doesn't matter. And let's just say that we are using the same search algorithm. Now, that's the first question. Do you think a search algorithm that will work with unsorted arrays, do you think that will work with a sorted array too? Yeah, it will work for a sorted array. It's just not very smart. Okay, let's see why we say it's not very smart. Okay, use the old algorithm to look for. Oh, let's make it very extreme. Okay, let's make this look very, very dumb using the algorithm that we had before. We'll look for -2. Okay, and we'll go ahead and copy and paste the algorithm so that we can refer to it when we talk about this. Okay, this is the algorithm. This is the array, and we are looking for -2. In other words, k equals to -2. This is our a bracket 0, 1, 2, 3, 4. This is our a bracket 5. So without actually going through a trace, okay, I can tell you what's going to happen already. I gets initialized to 0, and I is less than bar, and a bracket I does not equal to k. Because we know that none of these items will match k. So we are guaranteed that the second condition, or the condition on the right-hand side of the conjunction, is always going to be false. Okay. So we will first take a look at this item here, and then we say, nope, 3 does not equal to -2. Move on, I becomes 1. 6 does not equal to -2, move on. 10 does not equal to -2. 11 does not equal to -2. 25 does not equal to -2. And 36 does not equal to 32. And then at that point, I will become 1 more than the last index in the array. And then the first condition on the left-hand side will become false, and then we get out of the loop with the conclusion that the element is not in the array. The value is not in the array. But I said, that's really dumb. If I told you the array is already sorted in a non-decreasing order, and I still do something like this, that would be really dumb. Why is it dumb?
Doing extra operations.
Well,
Just stop it after the first.
Exactly. I could have stopped, after the first comparison, and why?
Because it's only going to get bigger after that.
Exactly.
So if it's greater than k.
Mm-hmm. Because once we compare to the first one, we are looking for -2, and the first element is 3 already, and the array is sorted in a non-decreasing order, that means everything to the right-hand side of 3, they all have to be at least 3. If they're all at least 3, they cannot be -2. And therefore, we could have gotten out as early as after the first comparison. Okay? So now the question is, how do we change this algorithm to take this into consideration? Okay, we can improve the algorithm to make use of the fact that the array is sorted. So if I copy and paste this code here, how can we, without worrying about the actual conclusion and just worry about can we get out earlier, how do we change this program to make it more efficient?
Can you include sorted in the while?
No, I cannot. What do you mean by including sorted?
Like, say while sorted and the other two, then.
The sorted part has to be assumed. So it is already assumed. I have to tell you ahead of time that the array is already sorted. So based on that assumption, how can we improve the algorithm?
Instead of saying not k, would you say less than k?
And a bracket I is actually the other way around. Let's see. If a bracket, okay, I think it's the other way around, you're right. If k is larger than the element, then we can still continue to look, yeah. Because, okay, but then I have to make it very explicit here in a non-decreasing order. Okay, because it depends on the order. If I tell you the array is sorted in a decreasing order, you have to flip the comparison because it impacts what you can assume about the other elements in the array. Great, this is good. We just made the algorithm more effective when we're looking for an item that is not in the array. But if you're looking for an item that is in the array, it's still the same thing. Okay, it will still have to go through the same number of elements, the same number of comparisons to conclude that, oh yes, the value that you're looking for is actually in the array. So it won't help you when you're looking for an item that is in the array. It will only help you occasionally when you're looking for an item that is not in the array. Is that how you look up a name in a phone book? We're still talking about sequential search here. So if you're looking for someone whose last name starts with a Z, you will still have to go through every single entry in the phone book until you get to the last portion of the phone book, which is not how we look up names in a phone book. Okay? So that means it's still not very effective because we can look for names a lot faster than that in a phone book. So you would expect a computer to do at least the same. So let's forget about this type of algorithm for the time being, and I'll just give you a question, and you can give me an estimate. Okay, it doesn't have to be exact. Just give me an estimate. What is the world population at this time?
6 billion.
6 point something billion. Okay. So if I have a global directory of every single person on Earth, okay, 6 billion entries or so, and I want to look for a particular person within that directory, how many comparisons do you think I will need? Assuming that phone book is sorted in a particular way.
As many as there are people. As many as there are people.
So 6 billion or something, comparisons. Any other guesses? What if I tell you the answer is 33? What if I tell you, if I have a phone book, okay, with everybody's entry in it, and it is sorted in the order, in a particular order, increasing or decreasing, using the key, okay? So the key can be a unique, ID of a person, but then I have to search by ID. It can be last name plus first name, then I have to search by, last name plus first name. But I'll just say that, whatever I use to search for a person, that particular thing is sorted in this particular table. I only need 33 comparisons to get to that person or confirm that person does not exist in the directory. 33. Okay? Does it sound impossible? It is possible, okay? Now, the reason why I can do this is because of this. So let's say this is a zoomed out version of the 6 billion something entry array, okay? Instead of searching from the beginning or the end, I look at the middle element. Now, why would I look at that? I look at this element here. I compare this element to what I'm looking for. There's a very slight chance, 1 in 6 billion, that this is exactly what I'm looking for. Most of the time, it's not. Now, on the other hand, because the array is sorted, just by one comparison, I can tell whether the element that I'm looking for is either on this half in the other half. The other way to look at this is I can toss away one half of this thing. So let's say I toss away this half here. Now I have half, or just 50% of what I started off with. What do I do with this half?
Same
The
thing.
same thing. I look at the middle one out of this half here, make a comparison, and let's say this time I can toss away this half here. I only have 1/4 of what I started out with. Now 1/4 of 6 billion is still a lot, but every time I compare, I only have 1/2 of the entries left. Okay, and that's exponential. If you think about it, that's exponential. In other words, if you look at the number of comparisons as n, I can cover 2 to the power of n plus 1, okay, that's a plus 1 deal here. I can cover this many items given only n comparisons. N to the power of 33 is already 8 billion something, and that's why with 33 comparisons, I can cover 6 billion entries or so in an array. Okay. Are there any questions about this approach? The general idea of this approach? No questions? Yep, go ahead.
So, is it 2 to the n plus 1, or is it 2 to the n plus 1?
2 to the power of n, and then that whole thing plus 1. So if I want to use parentheses, it is like that. And it kind of makes sense because if I only have one single item, I still need one comparison to confirm. So it's actually minus 1, not plus 1. I can cover this many items using only n comparisons. Because when I only have one item, I still need one comparison to cover that, to confirm whether that is what I want or not. Okay, so let's go ahead and use an example, because it's always better, when we use an example to illustrate this. And I'll just add one more example, one more number to make this kind of like a perfect match. So we'll just add, say 47. That's the next number. And I'll just kind of change the spacing a little bit so it kind of looks better when we do it. Okay. So let's just say that we look for a particular value that is not in the array, because it is harder to spot something that is not in the array most of the time. What do you guys want to look for that is not in the array? 5? Okay, let's look for 5. Okay, it doesn't matter what I'm looking for, because I always start from the middle of the entire array. So that means I will pick the 11, in this case, as my middle element and compare 5 to it. I will use the uppercase V letter to mean greater than. So in this case, I'm basically writing the greater than vertically and say that 11 is greater than 5. If 11 is greater than 5, which part of the array can I eliminate at this point?
The right side.
Everything above 11.
Okay. I can eliminate that side, right? Because the array is sorted in a non-decreasing way. So that means if 5 is less than 11, it is for sure also less than everything on the right-hand side of 11. Is that making any sense? And since it's always going to be less than all those elements, it cannot be equal to any of those elements, and I can just eliminate those from my consideration. I only have 3 elements left. Of the 3 elements left, I can use this one as my middle one. When you compare 6 to 5, 6 is also greater than 5. So that means I can eliminate everything, including 6, and everything to its right-hand side. I have 1 element left. With only one element left, I still have to do the comparison. This time I identify that 5 is greater than 3, And so I can eliminate 3 and everything to its left-hand side, but there's nothing else to the left-hand side. So at this point, I have eliminated every single element in the array. None of these elements can have the value of 5. Is that okay so far? Yep.
What would happen if you had 8 entries, so there was no
Very good question. I think you guys are starting to catch on to why I use exactly 7, because 7 fits into this pattern, and 2 to the power of 3 is 8. 8 minus 1 is 7, so it fits exactly. So when you have 8 elements, I will potentially need one more comparison to confirm it, because let's do it when we have 8 elements. So we'll just copy for the most part this whole thing, and let's just say that we have a -2 here, okay, as my first element, and we'll look for another number. What do you guys want to look for? 22. Okay. So same thing here. Now this time I can choose. Okay. When you have 8 elements, you technically speaking have 2 middle elements. In this case, the element with the value 10 and the element with the value 11, they're both considered the middle elements. And you can choose either one. It doesn't matter which one you choose, just pick one. Which one do we want to pick?
Let's just start with 10.
Okay, we want to pick the 10, that's fine. Okay, so we'll say we pick the 10 and then we identify that 22 is greater than 10. If 22, the value that we are looking for, is greater than the element that we are looking at this point, that means everything, including that element and everything to its left-hand side, can be eliminated, because everything to its left-hand side are smaller, and they will automatically be smaller than 22. So this time we eliminate these 4 elements to begin with. Now we are left with 4 elements on the right-hand side. So with 4 elements left on the right-hand side, we also have a choice, because 25 and 36 are both considered middle elements. Which one do you want to pick?
36.
Pick 36? See, the thing is, you don't even have to be consistent. Okay, sometimes we can pick the first one, sometimes we can pick the second one. It still comes up to be about the same, because it really does not matter. So we pick 36 this time, and we identify that 36 is greater than the value that we are looking for, which is 22. So that means 36 and everything to its right-hand side can be eliminated, because every value to the right-hand side of 36 has to be greater than or equal to 36, and 36 is already greater than the value that we're looking for. So now we have eliminated all except 2 values. When you have 2 values left, you can pick one or the other again. Okay, which one do you want to pick this time? Doesn't matter.
11.
Pick 11. Okay, so this time we compare to 11, and we identify that 22 is greater than 11, and that means we can eliminate 11 and everything to its left-hand side. And now we have only one element left, which is 25. So when we compare to the only element left, we have 25 is greater than 22, and that means we can eliminate 25 and everything to its right-hand side. And now we have eliminated every single possible entry in the array, which means it cannot be in the array at all. Okay, so this is binary search. The name is called binary search. It's one of the most interesting algorithms that we can talk about in this class in cisp300, because it is very simple, and yet it is also very powerful. Because what happens when the world population doubles? So it becomes like 12 or 13 billion. We'll have to, some people have to live on Mars at that time, but let's just say that we still have one single array for every single person.
It only takes one more iteration.
Exactly. It will take only 34 comparisons in that case to confirm a name is in the array or not. Okay? So that means it is a fairly powerful algorithm, because you can double the number of entries, and yet it only adds one more comparison, only adds one more iteration. Okay. Are there any other questions about the algorithm itself? No questions? Okay. So now that we understand the algorithm and we can do it by hand, the next question is how do we write an algorithm to do exactly that? Okay. Well, it looks kind of hideous, but it's not. It's not really as hideous as you think it is. Some people might have read ahead of me and actually know what it looks like. But we'll start with something like this. If you just look at the example that we have looked at this point, is it repetitive? Are we doing something again and again until something happens?
Yeah.
Okay, it seems repetitive to me. So as usual, if it is repetitive, I'll just say that in revision 1, we say this is a repetitive thing, it is a loop. So we say loop and loop. And remember when I say loop and loop, I just mean that it is repetitive, but we don't know whether we should use a pre-checking or a post-checking loop. It's just a loop of some kind. And when do we exit in this case? It is still a search algorithm, isn't it? We're still looking for something in an array. So that means what we used in the previous class to get out of a search algorithm with linear search still applies. Logically, it still applies because logically, we are going to get out when we have found the item, or we confirm that none of the items in the array can have the value that we're looking for. So that still works. But this time, the phrasing has to be a little bit different because we can say when the item is found, or we confirm no such item exists in the array. And this part is exactly the same as in the linear search algorithm. All search algorithms will have something that looks like this. Okay, in revision 2, we will start to think about, okay, but we know that this time the way we can tell whether there are still items in the array that can have this value, the way we keep track of that is different. Because before, with linear search, we start from the beginning, and then we keep going like this. So that means everything to the left-hand side of this index here, they are confirmed not to have the value that we are looking for, and everything to the right-hand side may still have the value that we are looking for. But this time is different. Okay, if you look at our example this time, okay, for every iteration, before the first iteration, everything can potentially have the value that we are looking for, which is 22. After the first comparison, this portion becomes the portion that may potentially have the value that we're looking for. After the third comparison, after the second comparison, we have 2 items left that may have the value that we're looking for. After the third comparison, we have 1 item left that may have the value that we're looking for. After the fourth comparison, then we have nothing left because we have just eliminated the possibility of anything in the array to have the value that we're looking for. So from this perspective, what is the difference between how we are keeping track of which portion of the array may still have the value that we are looking for? First of all, is that region still contiguous? In other words, are we saying that, oh, the item may be here or here? This would not be contiguous because the 2 chunks are separate. Or are they always contiguous, which means it is one chunk in the array?
Yeah,
It's still contiguous, right? It may not be starting from the beginning, it may not be ending at the very end, but it is still contiguous. Okay, when we look at these 2 items, they're still contiguous. So that means this time what we can do is instead of using one variable to keep track of the bookmark, okay, because everything on this side of the bookmark is already confirmed not to have the value, and everything to the other side may have the value. Instead of using one bookmark, I'll use 2. Because when you use 2 bookmarks, you can define the beginning and also the end of the region in the array that may have the value that we are looking for. So that's what we'll do. We'll basically identify 2 of these bookmarks. We'll use B to represent, B represents the index of the first item in the array that may have the value of K. Okay? That may equal to, and similarly, we'll use E to represent the last item. So E would represent the index of the last item that in the array that may equal to K. Okay, is that making any sense? I'm just using two bookmarks, two variables to keep track of the beginning and the end of the region in the array that may have the value that we are looking for. So if you look at our example here, initially the entire array. So that means B initially is 0 and E initially is bar A bar minus 1 because they are the indexes of the first and the last element in the entire array. After the first comparison, B becomes 4 because because array A bracket 4 is 11 and that's the first element in the array that may have the value that we're looking for. E on the other hand would still be 7 after the first comparison. After the second comparison, we only have this region left. So that means in this case, B equals to 4 and E equals to 5. After the third comparison, we only have one element left. So what do you think would be the values of B and E? 5 and 5 and 5. Very good. Because 5 is both the beginning of the index, it's both the index of the first element that may have the value that we're looking for, as well as the index of the last element because they are the same. What happens after the last comparison? Well, it's not exactly false because B and E are integers and you cannot put a false value into an integer. What happens is they overlapped. Okay, they just go across, they just cross each other. When they cross each other, then we say that that we don't have anything left. So we'll see in the algorithm how we do that. So given this representation, can we change the loop a little bit here and determine what to do? I think that's still a little bit hard to do, but we can expand to what we want to do inside the loop. Oh, by the way, how do I confirm the item is found?
Item equals K.
Okay, so some item equals K. Okay. So we'll just say that A bracket M equals K. Now I'm not using I this time, I'm using M, which is another variable to confirm that. And we still don't know how to express this thing here. We confirm no such item exists in the array. Can we do something about B and E? Do we know how to update B and E? Well, let's take a look at the example. Okay, the example is always kind of helpful. Okay, this is our original array. This is our comparison, and we're comparing to this thing here. The first thing we want to do is to say, we know this is B, okay, 0 is B, 7 is E. How do we come up with the index of the element that we want to compare to?
Divided in half.
It's the average, right? It's basically the B plus E divided by 2, okay? So that's kind of good because we now know how to compute M. Because M is the variable to control which item in the array do we want to compare to K. So I'll just say that, we can easily calculate M, and at this point, I'll just say something like this, okay? Which is not exactly right, okay, but it does capture the main idea, which is good enough for the time being.
This is because the index of the last element would be.
It's 7 in this case, so this would be 3.5.
But and the first one is 0, so you add them together and take the average, and you get approximately a middle.
Yeah, yep. But I'll just leave it the way it is. I'm just trying to make sure that I can get the main concept first. Okay. Okay. So how do we update B and E? Let's take a look here. If the number that we're looking for, K, is greater than A bracket M, what are we moving in this case? Okay. If you just look at the first 4 rows here, are we updating B or are we updating E?
B.
We are moving B. Okay, so maybe we can just kind of capture that logic here and say if A bracket M in this case is less than the value that we are looking for, then we want to update B. Right?
Right.
Else if A bracket M is greater than K, which is the other case here. Okay, the second case, is when it's 36, A bracket M is greater than K, which is 22. We want to update E instead because we are moving E to this point. E used to be here, and after the second comparison, the E is moved over here. And I can put an end if here because when they are equal, there's nothing to do. When they are equal to each other, I just wait until the loop picks it up, and then we get out of the loop. Okay, so we'll just leave it, as one. Leave this one as one revision already. So when you don't know exactly how to do something, you can always kind of defer that until later, but you want to capture as much as you can of what you know what to do at that time. So now we take a look at this algorithm and we say, can we improve that? Well, there are certain things we can do to improve it. We can start with initialization. This is our revision 1. That was 2. This is 3. So in revision 3, we can start to think about, because of this, we know that B has to start with 0, and E has to start with bar A bar minus 1. Is that okay? Because before the very first comparison, we don't know which part of the array can be eliminated. So we have to say the entire array may potentially have the value that we are searching for. And how do we say that? Well, the first element that can have the value is the very first element, which is A bracket 0. The last element that can have the value is A bracket A bar minus 1, and that's why E is bar A bar minus 1, because it is the index of the last element that can have the value that we are looking for. So that's kind of easy because given the meaning of B and E, we know how to initialize those two. Okay, how do we update B in this case? If you just look back at the picture, I think B has something to do with M itself. Okay? Kind of like this, but not exactly. Okay? Let's take a look, go back here and take a look.
M plus 1.
B plus 1. Okay? It's M plus 1. Okay? Because this is M, we're comparing to this element here, but B is actually one element past it. Okay? But why does that make any sense? I mean, why do we want to add 1 to it?
Because we already evaluated
A bracket M itself, exactly, very good. Because by this time, by the very comparison that is on top of that is in the conditional statement, we just confirmed that A bracket M itself is not what we're looking for. And that's why B, which represents the index of the first element that can have the value K, it cannot be M because we just confirmed that M does not match. That's why it has to be M plus 1. So if we know that B is updated to be M plus 1, can you guess what E is going to be updated to?
M minus 1.
M minus 1. Because once again, we just compared to A bracket M and know that it does not match what we're looking for. Everything after that cannot be what we're looking for. So the last item that can have the value K would be the element to this guy's left-hand side with the index of M minus 1. Okay, so this is good. Okay, this is starting to come together, and we'll just call this another revision. Okay, we haven't really resolved everything yet, but I think this is moving in the right direction. So we'll just copy and paste this code again to revision 4. Okay, in revision 4, what we want to do is to say, can we take a shot at how can we know that such an item does not exist in the array? I kind of have a feeling that we have all the variables that we need at this point. We have M, which is the index of the element that I'm comparing to. We have B, which is the index of the first element. We have E, which is the index of the last element in the array that may still have the value of K. Now, what do we know at this point? We know that B is always going to get bigger. Okay? Because B was originally all the way over here, E was originally all the way over here, and every single time we move B, it's moving in this direction. When we move E, every single time it's moving in the other direction. We know that at some point they will match. Okay, they can match because in one of our examples, they did match at a point. When they match, can I get out of the loop? No, because when they match, when they're exactly the same, we have one element left.
Evaluate.
But after that point, if the element does not match what we are looking for, according to this algorithm, what do you think will happen to those two? This is B, this is E. They get closer, they get closer. Yep, they will basically cross over. Okay? When they cross over, B becomes greater than E. Right? Because B was originally 0, and E was originally bar A bar minus 1. So when they cross over, it means B becomes greater than E. Does that make sense? Does it make sense that B is greater than E is telling us that such an element does not exist in the array? It does, because of the definition of B and E. Tell me again, what is the definition of B?
Beginning.
Is the index of the first element that may have the value of K. And what is the definition of E? Is the index of the last element. So if the first element has an index greater than the index of the last element, there's nothing left. Right? So that's why it makes sense in both ways. In both empirically when we look at these how B and E gets moved around, but it also makes sense when we look at the very definitions of B and E themselves. So that's why this is almost done. We are almost done with this entire algorithm. The only thing left to do is to determine should we use a pre-checking loop or post-checking loop. What do you guys think? When possible, we want to use a pre-checking loop, but in this case, can we use a pre-checking loop? We cannot use a pre-checking loop because if you use a pre-checking loop, which means this condition or if the negative version of this condition will be put all the way up here. What is the problem of putting this entire condition here up here?
First time we don't have an M.
Exactly, we don't have an M to begin with. So that means the body of the loop is helping us to set one of the variables that we need to determine whether we should get out or not. Let me just point out what I'm talking about here. This statement is helping us to determine this value here, which we need in order to know whether we should get out or not. So that's why it cannot be a pre-checking loop, because we just don't know what M is. Now, someone can go back and argue and say, yeah, but we can do another initialization after E gets bar E bar minus 1, and before the beginning of the loop, we can say M gets the average of the two. You can do it. It's okay to do it, but then you will be wasting one statement, because that statement really does not have to be there. So that's why in this case, you can make a pre-checking loop work by working around it, but it will become less intuitive. And that's why it makes more sense to use a post-checking loop instead, because it's already set up as a post-checking loop. And it just works naturally in this case. There's one more thing to fix. Okay? The other thing to fix is this part here. Initially, using the last example that we used, B is 0, bar A bar is 8, 8 minus 1 is 7. 0 plus 7 is 7. 7 divided by 2 is 3.5. I cannot use 3.5 as an index, because the index has to be an integer. So how do we fix that problem? You can use rounding. Okay, you can use rounding, or better yet, we'll just use the floor function. Okay. How many people know what is the floor function? Okay, the floor function is quite easy to define, and yet it can be confusing. The floor of x is the largest integer that is less than or equal to x. That's what it is. That seems pretty easy. Let's take a look at the floor of 2. What is the largest integer that is less than or equal to 2?
2.
Okay. 2, less than or equal to. Don't forget the equal to part. Okay. So the floor of 2 is 2. Fine. Okay. What about 5.67? 5. Very good. What about the floor of negative 2.67?
-2.
Aha! Gotcha. It's negative 3. Because negative 2 is not less than x. Okay? So this one is always preferring things on the left-hand side. But since we cannot use a negative number as an index, you guys don't have to worry about the last case, because it won't happen. Or hopefully it won't happen. Okay. So is that okay? Does everybody understand what is the floor of a number? Can you imagine what is the ceiling of a number? The ceiling of a number would be the smallest integer, the least integer that is greater than or equal to x. Okay. And we are done. We have the entire algorithm, the entire search algorithm. Okay. Now this is a good time, to kind of stop with the technical stuff and instead kind of talk about the concept of time complexity. Okay, which is a kind of fancy word of, how good is your algorithm. Okay. So let's just imagine that we have a situation, and I'm working for a software company, and so is, let's call the next person Pat. Okay, so Pat and I are working for the same software company, and the company, as most companies these days, are downsizing, right? So the boss said, I know this is really hard, but I have to let one of you go. And in order to decide who has to go, I'll give you guys a programming contest. Whoever writes the best search algorithm will stay in the company, and the loser will have to find another job. Okay, that seems fair and easy, right? Except the boss said, when I evaluate your search algorithm, I'll be using your own computer to evaluate the efficiency of your search algorithm. Now, Tech, being the old timer of the company, started off 8 years ago, and I have been using the same PC ever since. So 8 years ago, what kind of PC would I be using in 2002?
PDM?
Is the P4 out at that time?
No, I think it was
P3?
P3.
Okay, so I'll be using a P3, Pentium 3 at 1 gigahertz, okay, which is, by today's standard, is not a very powerful processor, but it's still kind of a good thing to do. I used to run virtual machines using my P3, and it worked fine. Pat, on the other hand, joined the company last year, so he has a quad-core processor using the Core I family, okay, which is really super duper, right? So Pat looked at me and go like, Tech, you're so going out of this company because of my machine will blow your machine out any day, anytime, anywhere, in any condition. I just looked at him and go like, just try, okay? So Pat, being so confident, decides to go online and search for an algorithm, okay? Because I don't need to come up with my own algorithm. I'll just go online and search for one. And most classes like this will introduce the linear search algorithm, which is the first search algorithm that we talked about, which is, let's see here, we talked about this, which is this one here. And let's say even Pat is even so smart that he figured out that, if the boss said the array is sorted, I can use the improved version. Okay, and Pat is so happy, his programs runs, and it's in very short, it can find the result in very, very short amount of time. Okay, and me, on the other hand, remembered, when I took a class in algorithm design, someone said the binary search algorithm is more efficient, so I kind of started with this algorithm over here. Pat took a look on my screen and go like, whoa, that is way too complicated. Look at my algorithm. It has fewer number of lines, and my machine is faster, so I don't think we have to, there's no competition here. Okay. So let's just take a look at the amount of time that each algorithm took in order to run the programs. Okay. So we have a little table here. I can do it online too. Let's do it on the online here using OpenOffice. Office. Okay. So this is me, this is Pat, and we are trying to measure how much time it takes to find an item. And this is n, which is the size of the array. Okay, let's use bar a bar, that's the best notation. When the array only has one element, and the element is, let's say, in all cases, the element is not in the array. Okay, we're searching for something that is not in the array. In this case, Pat and I will both have to perform one comparison to confirm that the only element in the array is not what we're looking for. So I perform one comparison, but when I perform one comparison, I will just try to measure everything in microseconds. because I have such an older machine and whatnot, on my machine it took 100 microseconds. Okay, I'll just make this really exaggerated. On Pat's machine, it took far less time. Let's say only took 1 microsecond to do it. Okay, which is about right. An order of having a difference of 100 over 8 years is about right. Okay. Okay, fine. Pat said, I won, you lose, you go. I said, no, hold on a second here. Let's make the array a little bit bigger. Okay, so we make the array bigger. I make it 3. The boss gave us an array of 3. Let's say Pat's algorithm on the average will take 1.5 comparisons because sometimes he can use the shortcut and sometimes he cannot, depending on the value that he's searching for. My algorithm in this case, how many comparisons do I need? I need 2 comparisons, right? Because 2 to the power of 2 is 4, 4 minus 1 is 3. So my algorithm took 2 comparisons. It took 100 microseconds for 1 comparison. So with 2 comparisons, I would need 200 microseconds. Does it make sense so far? Okay. So, Pat said, you lose, I win, you go. And I said, no, hold on a second here. Let's make the array bigger. Maybe that will help me. And Pat said, sure, that's going to help you. All right, let's bump it up to 7. So he, in his or her algorithm, it will now take an average of 3.5 microseconds because sometimes it's the first one, sometimes it's the last one. So on the average, he has to perform 3.5 searches. In my case, it will take me 3 comparisons because 2 to the power of 3 is 8. 8 minus 1 is 7, and I'm still losing. But you can see at this point I'm kind of closing the gap a little bit here. Okay. So we bump it up again. This time I'll bump it up to 15. So in his case, his algorithm will take 7.5, and my algorithm will take 400 microseconds. So you can see the number is, even though I'm still losing, the difference, the gap is closing. Okay. So if I bump this up to 31, what do you think Pat's algorithm will take? 31 divided by 2. Right? Because it's just the average. What about my algorithm? How long do you think my algorithm is going to take? Okay, it's going to be 100 times the log of this number divided by the log of 2. And I think that's off a little bit here because I have to remember to do a subtract. Add 1 first. Okay. So what I have done now is I can now magically extend this table without having to do all the calculations by hand, because now I can do something like this. Okay. No, that's not what I want. Nope. No. This is not what I want.
I'll do this sequential.
Yeah, because I want to change the power. So over here I need to put the power of 2, and this becomes 4, and that becomes 2 to the power of, I'm not sure what, do you know whether this is the power of symbol?
Should be.
Yep, it is. That's not the case though. What did I do wrong here? 0, I should start with 1. No, it's still not. 2 to the power of 5 is 32. Is it? Why is it wrong?
Maybe the 5 minus 1 is getting order of operations. So.
Oh, right. You would think that the power of is, no, that's the right orientation. It's not working. But anyway,
Just make the number a billion.
if you make this number big enough, I will win. Okay, and how big is big enough?
A billion. That's pretty big.
I don't think we'll need that much. I'm pretty sure that I can win without making that number that big. Okay, let me see if I can still make this happen. So So we'll say equal to 2 to the power of. Oh, okay. I think I know why. Operator error. That's why. There you go. Okay. So I won when only there are 2,000 items in the array. When it got up to 2,047, well, okay, maybe the next one. The next one. When it got up to 4,000 items in the array, I look at the pattern and go like, well, let me show you the door. And guess what? I'll be taking over your PC too. All right, so that's it. But I hope you guys understand the importance of the method of the algorithm and not just the raw power of the machine. So this will be tag. That's it.
Did you get a sign-in sheet?
No, I did not bring a sign-in sheet today. So you guys are good. But this stuff is important because, it doesn't seem it's important, but, when you look at it, a search algorithm is not really a search algorithm. If you pick the wrong one, it can change the amount of time it takes to execute the algorithm. I cannot find my command prompt. Did I close that accidentally? Oh, that would not be good.
That's true. There were a number of different people competing, like different teams competing on finding like pi to billions of decimal places.
Yep.
Or was it millions? Well, millions, billions. Yeah, it was down to billions eventually. And it was like a ridiculous number of doing. You need a supercomputer to crunch that kind of thing. And the guys that won were these